We're going to continue on the theme of trying to solve ax equal to b in the fastest possible way we can. And what I'm now start talking about are fast Poisson solvers, and particularly those that use or leverage the fast Fourier transform. So when we're solving large ax equal to b problems, often the real issue is that ax equal to b is order n cubed to solve in computational speed, which is, as n gets very large for these very large matrices, it becomes computationally intractable. The fastest solvers on the market, in terms of if you can use them, is using the FFT, or the fast Fourier transform, which can solve those problems in n log n time. So this is a massive computational savings, and anytime you can use the fast Fourier transform to solve some of these, you absolutely do. It's just faster than almost anything that you could possibly do. Second is the iteration schemes that I've just talked about, and so these are two of the techniques trying to circumvent the cost of the order n cubed solve. And even if you do an LU decomposition of that matrix to get it down to the LU, it's still order n squared, and that still becomes prohibitively large. So what you're really trying to do is, can I get below that order n squared mark? And so the fast Fourier transform is n log n, which is a massive improvement in speed. So first of all, how does it work? So remember, we're solving this here. We're solving the Poisson equation for the stream function and related to the vorticity. So if we write this out, right, we can look at this and we can start thinking about, I've got to take two derivatives in x and y. So let's start thinking about how I might do this with the Fourier transform. So here's what the definition of the Fourier transform pair is. So if you take a function of x here, and you can multiply by e to the minus kx, square root of 2 pi, and you put yourself in the Fourier domain. To come back from the Fourier domain, you have e to the ikx. So these are opposite signs, and you integrate and come back. There's different definitions of the Fourier transform. Some come out with just 1 over 2 pi instead of coming in and out with square root of 2 pi. So it depends if you look at sort of the physics literature or the engineering literature. They often define the Fourier transform in slightly different ways. And so just keep that in mind. This is not a unique definition of the Fourier transform, but it is a Fourier transform pair we can work with. So what I'm going to do with this, I'm going to show you that if we use the Fourier transform, there's this very nice, one of the most important properties, in addition to n log n speed to produce the Fourier transform, is the derivative properties. So let's take the Fourier transform here of the derivative of f of x. So f prime of x is the derivative. So I Fourier transform it, which is represented by the hat. So just throw this in to that integral definition, and what we do here is we just do essentially, right, we're going to just do substitutions. We're going to basically take f of x, and we're going to do a substitution rule here, integration by parts. And integration by parts is one of the most useful things that we learned in actually all of integral calculus. Is we're going to do integration by parts to get out this piece here. You're going to assume that the function goes decays at plus or minus infinity, so this will go to 0. And what you're left with is here. And what you end up with then is the Fourier transform of the derivative of the function is equal to ik times the Fourier transform of the function. This is a very powerful relationship. So it means that all you have to do to understand what the derivative is, you just multiply by ik. And if you actually go and do this over and over again, the nth derivative just pulls out ik to the nth power. So think about how easy it is to differentiate a function now. All you have to do to differentiate to the a fifth derivative is you take the function, you put it in the Fourier domain, you multiply ik to the fifth power, and then you pull it back from the Fourier domain. So it's n log n in, n log n out, and all you did is multiply by this term when you're in the Fourier domain. So it's a very convenient way to estimate derivatives. How can we make use of this in terms of this Poisson equation that we have to use to solve the stream function? Well, so first of all, I'm going to give you one more example of how to do it, solve a differential equation here. Here it is. And we're going to solve this differential equation using Fourier transform. So you have two derivatives, minus omega squared y, and some forcing. So we're going to first of all put it in the Fourier domain. So when you put it in the Fourier domain, you're taking the Fourier transform of the second derivative, which is you pop out an ik squared is negative k squared. So the I squared makes a negative 1, and you have this. And now this just becomes algebra. Now you just solve the algebra for y hat. And this is the expression you get. and then you just invert it. So once you've got this in the Fourier domain, all you have to do is the inverse Fourier transform of this, and you have your solution. And it's kind of as easy as that. And in fact, it follows very much with the theme of how you typically solve differential equations. You plug something in, you plug in an exponential type solution, whatever you want to do there, you turn the ODE into algebra, and then you come back. And that's exactly what this does here. But now you're using the Fourier transform to essentially do away with your derivatives. In the Fourier domain, it's just a multiplication by ik. So how do we go and solve our equations here for the fast Fourier transform? We want to think about this Poisson equation. And remember, this is 2 derivatives in x, 2 derivatives in y. So what we're going to do to solve this is we have to take a Fourier transform in x and then a Fourier transform in y. So let's do that. We're going to walk ourselves through it. So first of all, take this equation, take the Fourier transform in x. So the Fourier transform in x will be denoted by the hat here. So if I take the Fourier transform in x of this second derivative in x, what's going to happen is that's going to pop out ikx squared, which is minus kx squared. The I squared become -1. They have this. And by the way, since we're taking the Fourier transform of x with the y derivatives, x and y are independent, so this just goes through. We just now take the y derivatives of the Fourier transform of x. Now we take the Fourier transform in y. Now when we do that, well, the Fourier transform in y is a tilde, so now I have to take this Fourier transform in y, which pulls out iky squared, which is -ky squared. There we have this, and then we just have algebra to solve. There it is. That's our solution. So notice what we have here is, with the Fourier transform, we've turned this just to an algebra expression. So if I want to solve this, I take the vorticity field, I Fourier transform in x and y, which is right here. I divide by kx squared plus ky squared minus sign, and then I just do the inverse Fourier transform. So I come into the Fourier domain, do some multiplications, come out of the Fourier domain, and I have 2 derivatives in x, 2 derivatives in y, and I've solved the Poisson equation in n log n time, because it takes me n log n to get in, n log n to get out. Okay? And that's it. That is the basic architecture of solving the streamline function from the vorticity using a fast Poisson solver. The fast Poisson solver usually is referring to the FFT because that's kind of basically the fastest guaranteed way to solve this AX at scale. And so anytime you can use a fast Poisson solver, you do, because this is just the fastest way you're going to be able to solve those problems in general.